In this video, we'll be looking at a different type of centripetal force. We're going to be looking at the forces acting on not a horizontal circle, but a vertical circle. These types of problems will typically deal with roller coasters and things that go in loop-de-loops. In this case, though, we're going to start a little bit simpler. We're going to start with a mass on a string being spun in the vertical circle, and we're going to look at two specific places. We're going to look at the top of the path and the bottom of the path. So at the top of the path, we have, obviously, the force of gravity acting downward on this object. But as we said, with any object moving in a circle, there has to be a force keeping it moving in a circle. So in this case, we see that gravity is pointing towards the center of the circle, but they gave us some other information. It's on a string. So what other force do we have to add to this picture? We have to add a tension force. So both of those forces are going to cause us to reach the center, to cause us to feel a force towards the center. Okay. At the bottom of the path, we have still the force of gravity, but in this case, which direction is tension pointing? Well, we're going to still be center seeking, and right now, gravity's not helping us reach the center. We're still going to have that tension force that's going to pull us towards the center. Okay. So that's the picture that we're going to look at for right now. So we can calculate the centripetal force, or essentially the net force of what's going to allow us to be feeling like we're being moved towards the center. So at the top of the path, as we can see, both of these forces are in the same direction. Remember, when we're in the same direction, we just add them together. So we're going to have tension plus the force of gravity. Now, if you would like to argue with me that they're both in the negative direction, please do. You can as equally say that negative T minus Fg equals the centripetal force. Just keep in mind that we are in the negative direction. That force, if you do calculate a number, should help us find the overall force in the negative direction. At the bottom of the path, on the other hand, we have the same two forces, but they're acting in opposite directions. So in this case, we're going to have T minus the force of gravity. Remember that in both of these cases, F of G are equal because it's the same object. So we're going to jump right into a few examples. We already have all the tools that we need, so we can go ahead and get started. Here we have a 1.7 kilogram object swung from the end of a 0.6 meter string in a vertical circle. If it's moving at 3.43 meters per second, what is the tension in the string at the top for part A and for part B at the bottom? So for part A, I'm not going to draw another free body diagram. It's the same as the top. So we're going to simply be looking at Fc is equal to the tension plus Fg. So before we get any further, let's look at what they gave us. So we know that we have a mass of 1.7. We know that we have a radius of 0.60 meters and a velocity of 3.43 meters per second. We do want to solve for tension, and tension is a force, so we will have a unit of newtons. By simply rearranging this equation, we know that tension will equal our centripetal force minus the force of gravity. So what I'm going to do is I'm going to substitute in everything that we know up to this point. So we know that the centripetal force is equal to mass times v squared over r, which is just the centripetal acceleration. And we're going to subtract force of gravity, which is mass times gravity, the acceleration due to gravity. So from there we can plug in our numbers. So we have 1.7 times 3.43 squared over 0.6. Then we're going to subtract the same 1.7 but this time multiplied by 9.81. Okay, and if you plugged it into your calculator correctly, you should reach an answer of tension equals 16.66 newtons. Okay. So that's the tension of the string at the top of the path. The next one we'll be looking at is at the bottom of the path. So I'm going to try to keep some of this information up here for us. Most of our knowns have not changed, so I'm not going to rewrite those. And we have our free body diagram at the top of the first page. The only thing this changes is our F-net equation. So in part A, we added them because they were going in the same direction, tension plus the force due to gravity. When we're at the bottom of the path, tension and gravity are subtracted because they are moving in opposite directions. We're still looking for tension, so to rearrange this, we'll add f of g on both sides. We're going to substitute in what we know, and so we know that f of c is mass times v squared over r. This is still that centripetal acceleration, and we're going to add m times g, which we know is the force due to gravity. So if you look, this here is identical to this with the exception of the sign change. So when you plug in your numbers, it should be this exact equation, but adding instead of subtracting. So I'm going to quickly jot that down. And if we plug it into our calculator, oops, this is plus. I made my own mistake. So we have plus here. I need to bring the plus down with you. Okay, so we should get something about 50. I have 50.01 if you'd like to be a little bit more precise. So I do want to make a quick note about these two answers. So at the top of the path versus the bottom of the path, which one has the higher tension? The bottom one. So think about it. If you had to twirl an object in a vertical circle, where do you need more force on the string? Well, at the top, gravity is helping you make that directional change. Gravity is assisting you in your centripetal force. At the bottom of the path, though, gravity is working against you. Gravity wants to pull the object down while the tension has to work harder to pull it up to make that directional change. So that's a good sanity check, something just to look at and notice. For our last thing, we have one special case where we might see in a problem. This is a good problem that's often asked. A lot of times this will be involved with a roller coaster. If we spin an object with just enough speed to keep it moving in a circular path, so just enough speed, so the bare minimum speed that we need, we're actually going to say that our tension is equal to 0. Okay, so why is that? So if we think about that free body diagram, at the very top of the path, we already have gravity helping us out. Okay? Tension is just there to make it a little bit easier, but it's not necessary to keep you going in the center of the path if gravity has enough, if you're moving fast enough so gravity can provide that centripetal force to help you make that directional change. Okay? Imagine when you're on a roller coaster and you go through the top of one of those loops. How do you feel? you feel almost weightless at the very top. It's when your stomach starts doing funny things. We say that the mass at the peak of an arc is weightless because the net force acting on it is only gravity. There should only be gravity acting on you at the top of any circular path. This is the same as an object in total free fall. So the same feeling that you get at the top of a roller coaster loop is the same thing as if you were falling freely through the air. Kind of a scary thought, but thankfully for roller coaster engineers, we are always safe. So I do have one quick last example just to show you how you would use this minimum speed problem. Okay. Here we have an object still swung in that vertical circle. We have a radius of 0.75 meters. What's the minimum speed of the object at the top of the motion for the object to remain in circular motion? So at the top of our path, the only force acting on us is F of g. So our centripetal force will equal our gravitational force. Okay? So let's plug in what we know. We know that F of c is m times v squared over r, and that's equal to mass times gravity for F of g. Now I wanted to do this first to show you something before we wrote out our knowns and unknowns. Looking here, what cancels out? Your masses. This does not depend on your mass. Okay? We said before that acceleration doesn't depend on your mass, and here's another case where that is true. So if you're thinking, well, yeah, they only gave us the radius, how could we possibly figure out this problem without any more information? Well, we can, and that's the beauty of it. So we know our radius is 0.75 meters. We know what g is by default, and we're just looking for a velocity. So we have to rearrange this problem. I'm going to do it in one quick step and then explain it. So if we rearrange this, we should get v is equal to the square root of r times g. Okay? Well, the square root should seem obvious. If we're looking for v and it's squared, we will have to take the square root at the very end. In order to get v squared by itself in the first place, though, I have to multiply this r on the other side. So I multiplied by r first and got rg, and then I took the square root of it. Okay? So this becomes a very simple 0.75 multiplied by 9.81. And I got 2.71 meters per second squared. Oh, not squared. It is not an acceleration. It is a velocity, so there should be no square on that unit. So this is a special case of circular motion. This method should only be used if you have this phrase, minimum speed. If you have the phrase minimum speed, the only force acting on it is the force due to gravity.